Okay, so let me give you a rough sketch how the bending moment distribution differs under earthquake lateral load, I mean wind or earthquake load, and how it uh, looks like in the gravity loads. So let's say under the gravity loads, if you have, let's say, this is the equivalent frame that we have been talking about. At the point of contraflexure mid height, so as you know, the moments in the beam because of the gravity loads would be somewhat like this, right? So the point is, uh, the beam in the interior beam joint, the moment here at the end of a beam is primarily balanced by the moment at the adjacent beam, moment coming from the adjacent beam. So the counteracting action is always beam to beam, right? This is not the case when you look at the moment pattern that arises because of lateral loads. In the case of lateral loads, there are lateral loads here, and this leads to column moments. Okay, I'm drawing on the wrong side actually. Drawing on the tension side. So this is what it is going to be. And the moment on the beams would also be uh, like something like this. So primarily the moments in the beams, uh, beam ends, is balanced by the moments in the columns at the top and bottom ends of the columns, right? Which are meeting the beam junction at that point, beam column junction at that point. So that is why that again reinforces the difference between uh, gravity load behavior and the lateral load behavior during earthquakes, and also why it is so important to preserve the column integrity in case of earthquake resistant design. And that brings us to the today's discussion: how do we preserve the column integrity, right? What do we need to do to preserve the column integrity? First thing is, how do you, in case of monolithic construction, beam and slabs are cast together. Isn't it? That's where the concrete is poured simultaneously. It occupies the beam formwork and also the slab. So it is poured at one go. So when you consider the bending moment or the strength design of this beam, do you really consider this contribution of the slab? Obviously, it's a monolithic construction, so it is not that only the beam portion is going to contribute whatever width of the beam that you have calculated. So we can look at, T beam and L beam end at the end. It will be an L beam, and in the middle it will be T beam section, and effective flange widths we can determine, and we can accommodate for that design. But quite often we ignore that in case of gravity loading, because that is only going to add to the strength. So for simplicity we can afford to ignore that, and no harm is done. That will only add to the strength of the structure. And if we design ignoring the flange action coming from the monolithic construction of beam and slab, then we are actually erring on the side of conservation. But this assumption of neglecting contribution of let's say effective flanges. There would be some extent of the slab which will be effective as the flange for the beam. This is conservative for gravity load design, but this is, I would rather make it more dramatic, disastrous for earthquake resistant design. Any ideas why do I say this? I mean, how can something that is so good and so desirable for gravity load can turn out to be disastrous for a different load condition for the same material?
Sir, in gravity load design, basically that flange we are considering is adding to our strength. But in earthquake, since the direction varies from one direction to another, sometimes it may be adding to strength and sometimes it may be adding to load. So removing it may means cause problem.
Uh, so what may cause problem? So by ignoring it, how does it cause a problem? If it is not there, then we do not account for it. So the beam width, that is what participates in the action. That is what we assume. So in what way is this going to be a concern?
सर जैसे कि अगर वो फ्लैंज है हम इनर्शिया फोर्सेस कंसीडर करते हैं ना ग्रेविटी में मतलब इनर्शिया फोर्सेस जब सब कंसीडर करने लगेंगे और किसी पर्टिकुलर पार्ट को छोड़ देंगे तो वो इनर्शिया
Ravi, there is no neglecting mass for calculation of inertia. That lateral load analysis, the lateral forces that you compute has taken care of all the mass. So for calculation of mass, we do not ignore the flange. I am coming. I am arriving at the flexural strength. So normally we ignore the flexural strength contributed by the flange action, and that is conservative for gravity load design. But my statement here is that by ignoring it, and that is why it is so critical to discuss, ignoring that contribution of flange action to flexural strength is disastrous for earthquake resistant design. So I want you to think about it and suggest, I mean, that's how you will develop the critical inquiry into this process of earthquake resistant design. So what is happening here which is making it disastrous? Again, the bottom line of earthquake resistant design, I have been repeating almost in every lecture, is strong column weak beam, and that is a hint. Okay.
सर
Yeah, yeah.
आई कैन ट्राई वंस सर वो जैसे अगर वीक बीम हमें बनाना था और हमने पी बीम हमें एक्स्ट्रा कैपेसिटी देती देती तो उसके रेस्पेक्ट में कॉलम को हम ज्यादा स्ट्रांग बनाते लेकिन जब पी बीम को हटा के हम नॉर्मल बीम कंसीडर करेंगे तो मान लीजिए वो पहले 80 कैपेसिटी था अभी 50 देगा तो कॉलम को हम 50 से ज्यादा बनाना चाहेंगे जो कि हमारा प्लास्टिक ही डेवलप कर देगा अगर हमारा वीक कॉलम बन गया तो
Exactly. So that's the problem. By ignoring contribution of flange, we underestimate the maximum capacity of the beam, and we obviously make columns to resist moment higher than the beam capacities. Now, if the beam capacity is underestimated, and whatever capacities we provide in the columns, that may actually turn out to be lower than the actual capacity of beams when we include the flange effect, right? So the mechanism, although we assume that it is going to be a strong column and weak beam construction, the hinges should form in the beams first, but if the actual capacity that is participating, actual flexural strength that involves contribution from the flange turns out to be more than the capacities of the column, then obviously the columns will develop hinge first. And no matter what you assume in your calculation, it is the actual behavior that governs the response. And we will be looking at portal mechanism and complete collapse of the structural system. So this is a very critical point that you need to understand, that we need to actually, we don't lose much. We actually try to make structure stronger by uh, erring on the conservative side, by estimating the including the effect of flange reinforcement, effective flange uh, in the flexural, in computation of the flexural strength, available flexural strength of the beam, and then provide the column capacities accordingly, right? So just ignoring two different load cases and leading to two different conservative design assumptions. In the gravity load, it is simpler to just go with the normal beam width and go ahead with the design without it accounting for flange widths, and it is fine. You should be good enough without any problem. But for earthquake load, earthquake resistant design, the neglecting flange effect is actually going to land you in trouble. It is not okay to ignore the flange width while calculating the flexural capacities of the beam. And next thing is the difference in the moment. See, the difference in gravity load is it's dominated by the positive moment at this near the center of the span. The negative moments are generally not very large, particularly when the uh, spans are long, right? For short spans, the negative moment and positive moments, they are both more or less of the same order. But for long spans, the positive moments will be very, very much larger than the negative moments. Contrast this with the earthquake load pattern. The it is the negative moment which is really large, and the signs may alternate. I mean, at one moment it is, one instant it is like this, next instant it is going to be like this. It will reverse the signs. So point is, you need to provide for uh, these negative moments at the supports, and they decrease very rapidly as you move away from the support, as you move away from the column beam column face, right? The maximum negative moments are at the beam column face, and they decrease very rapidly as you move away from the beam column face. So hardly there is a issue of any concern of plastic hinge being developing in the uh, mid span. So the beam sway mechanism should aim at uh, plastic hinges near the column face. That is where the maximum moment happens, and because it is reversible moment, the signs can go back, positive, negative, and gravity load in that case, this effect of this negative moment is not going to be of that much significance, although we need to once we redistribute it. So we need to provide almost similar capacities on the both sides. So and then obviously then it ends up being doubly reinforced section. for reversible nature of loading. So at all these beam column junction, you will find that the maximum negative moment is on the top fiber at one instant. At the next instant, it goes to the bottom fiber. So obviously, you need to build the capacities at both sides, and the flexural capacities are of course dependent on the will be governed by the steel properties. The tension, the steel has to yield first. I mean, the yielding has to happen in the reinforcing steel. So, what is tensile steel at one moment becomes compression steel at the other end. And now, what happens when the steel yields? Why do I say that the it, it is better to avoid the advantages? I would say preferred locations for development of plastic hinges is a little distance from the beam column face. Now, why do I say that a little away from the beam column face? Because maximum moment, of course, happens at the beam column face. So, why to move away from the beam column face? Any ideas? And avoid development of plastic hinges in midspan. This is because cracks may not close fully under load reversal. So if the hinge forms somewhere, uh, it is to be avoided, but if it cannot be, sometimes it may happen that situation is such that you cannot avoid development of plastic hinge here. So the point is, because of this large moment, large positive moment here, by the effect of load reversal, you may not see any sign change, uh, change in the curvature at this location. So the rotation, the sections, the cracks that have developed here, flexural cracks, they may not actually close fully under the effect of load reversal, and that may lead to another set of cascading set of problems, because reinforcement gets exposed, and then all sorts of things start happening, and leading to very rapid deterioration of the section capacities. So that is why it is better to avoid development of plastic hinges in the middle of the span somewhere, where there is very little moment due to the earthquake load. And moment due to earthquake load, maximum flexural capacity is actually needed. Maximum moment actually happens at the beam column face. So why should we provide plastic hinges. How do we provide plastic hinges? A little distance from the beam column face when the maximum moment occurs at the beam column face. Any thought process on this?
Sir, that can be provided by using a tapering phase, means more depth at beam column interface and less at a point far away from the beam column interface. By this way, we can do that.
Yes, hunched beam is one way to go about it, but it is very difficult to construct. Formwork costs increase substantially. It is not easy to develop formwork for casting a hunched beam. So theoretically, yes, and also the slope of that uh, taper of the hunched end is very critical. That has to be decided. So theoretically, yes, that can be uh, done, but rarely adopted in practice. But the basic idea is right. You increase the capacity at the beam column face, and the reason why we do not allow any plastic hinge to develop, why it is not desirable to develop a plastic hinge at the beam column face, is that the yielding of the steel will extend into the beam column joint, beam column junction, and that will lead to deterioration of the bond, and that will adversely affect the shear capacity of the beam column joint itself. And that is where we actually, beam column joint is a very critical component that is not easy to repair. That is absolutely uh, so to say sacrosanct, uh, that its integrity cannot be compromised at any point of time. So we will come to the design of design issues in the beam column joint a little later, but very high shear strength is required in the case of a beam column joint, and any yielding, any progression of the steel yielding inside the beam column joint is going to adversely affect the capacity of the joint, and therefore we try to move it away, development of the plastic hinge a little away from the beam face, beam column face, typically one effective depth, or if it is too deep beam, then probably 50 centimeter from the beam column face. So that is where we try to relocate the plastic hinge, and the way we relocate is we increase the flexural reinforcement in that range up to one effective depth from the beam column face, and then the reinforcements are anchored 90-degree bend, and then their top fibers go into, are bent to continue as bottom fiber, bottom reinforcement, and bottom reinforcement are bent to continue as top reinforcement beyond the point of curtailment if required, and that is what gives you the uh, adequate, I mean large flexural strength at the beam column face, so that plastic hinges will not be developing there, and the plastic hinges develop at a distance away from the beam column face, which is desired. And then the plasticity has to be extended over a length. It cannot, I mean, it will lead to very high curvature ductility if it was to be all inelastic deformation was to uh, occur at 1.1 section only, right? So that is why it is required. So plastic hinge, inelastic deformations, in tension reinforcement should happen over a length, right? Otherwise, if it happens only at a localized uh, yielding at one section only, will lead to a very high localized curvature ductility demand. And that may lead to lot of difficulties. Uh, Very high curvature ductility demand, that means the rotations are going to be excessively large, and uh, concrete may get crushed, and reinforcements may get exposed yield at that particular location, and very severe deformation and sagging will be observed, and leading to lots of serviceability issues. So, in order to prevent, so the flexural strength, ideally flexural strength, flexural cracks that you see during the inelastic deformation because of the yielding of tension reinforcement, obviously that will lead to cracking in the concrete. Uh, Slip should not happen. We should try avoid any bond failure, so the concrete may crack. So the cracks should be distributed over length, and that is what the plastic hinge length that should actually go up to twice the 2 times the effective depth. And in the plastic hinge location, the length of the plastic hinge approximately 2 times effective depth, and special reinforcement detailing is required. Is needed in the plastic hinge region. And when I say plastic hinge region, special reinforcement detailing is required. It doesn't necessarily, it doesn't limit itself to not only confining steel, confining or transverse steel. See the transverse steel, why do you use transverse steel? Why do you use transverse steel in beams?
resist the shear,
Pardon?
to resist the shear force.
Resist the shear force. Uh, And where do you have the maximum shear force, or what is the shear force where you have the maximum moment?
At a maximum moment, sir, shear force zero.
Shear force is zero. And where are we providing this? Where will the plastic hinge form?
Where there will be maximum moment.
So where there is maximum moment, or we are moving away from the beam column face. Beam column face is where the moment is going to be maximum. So little away from that. So the shear force is still is going to be very small, isn't it? It cannot develop. It cannot develop into a large number suddenly from zero value. So the moment is maximum. So shear force is small, and still we provide more transverse steel in plastic hinge region. So that confinement, that is to provide the confinement to the concrete core, right? So the shear strength is automatically taken care of. The transverse steel that we are providing in plastic hinge region is not to account for the shear resistance. Shear resistance obviously is the side effect, because there is not much uh, shear force there to speak of, because it's the region where the bending moment is maximum, so the shear force is obviously not going to be very large. So we provide those transverse steel primarily to increase the confining pressure, so that the we can achieve large curvature ductility. The compression strain that the concrete can withstand is increased considerably, almost by a factor of, I mean, the ductility increases by a factor of, I mean, 5 or 6, the compression maximum peak compression strain that you can have by using this confining reinforcement. And that is the primary reason for doing that. At the ultimate, the idea is to achieve as large curvature ductility as possible, and for that, in order to achieve large curvature ductility, we need to ensure that the cracking strain of the concrete under compression also needs to increase. Otherwise, without confinement, the cracking strain is only 0.0035, and not much ductility can be achieved. So by using those special confining reinforcement, transverse reinforcement, we achieve that. But that is not enough. We also need to put limits on the flexural strain, flexural reinforcement. So there has to be not only confining reinforcement or transverse steel, there are there has to be some minimum and maximum limits on the flexural reinforcement. So certain minimum flexural strength is required, so that we are guaranteed that the flexural strength, because of steel yielding, is actually more than the uh, cracking strength of the concrete, right? So that we do not, the material doesn't really fail suddenly. And maximum flexural reinforcement is again required to ensure that certain minimum amount of curvature ductility is guaranteed. Too much reinforcement obviously will not allow any ductility to develop, and that will be counterproductive for energy dissipation in the earthquake resistant construction. And so both minimum flexural minimum limit on reinforcement on flexural capacities, and the maximum limit on the reinforcement that can be provided. And of course, there is also the requirement that compression reinforcement has to be greater than or equal to 50% of the tension reinforcement at any point of time. So this is something I mentioned earlier. I was talking about the positive moment capacities have to be at least uh, equal to or more than 50% of the negative moment capacities at the any point. So that is more correct statement would be the compression steel reinforcement uh, has to be at least 50% or more than the of the tension steel reinforcement at any section wherever you look at, right? So that will ensure this uh, upper limit, upper bound and lower bound uh, will generally ensure that the proper curvature ductility, minimum curvature ductility is guaranteed. You can look at these numbers. What are these numbers? These are empirically derived numbers uh, based on experimental observations, and you can find those figures from the or the expressions, empirical expressions in various books. What is the maximum limit and minimum limit, and those provide the basic uh, margin of flexural reinforcement, and with that we can go ahead with the flexural design. Now, as I said, the capacity, I will tell you, as Ravi said, we can have this kind of reinforcement detailing. To ensure that the moment so this XX section, this is where the plastic hinge starts. So beyond this we move away from the column face. So this haunch and additional reinforcement here, this increases the uh, capacity of the section here. So the it doesn't yield, but the yielding will happen at this point, and it will propagate over a period of this plastic hinge region. Okay, not here. So this is the plastic hinge region, and that is where you need maximum curvature ductility, and the spatial confining reinforcement is required to increase the uh, concrete compression, higher compression strain that it can accommodate. And the other detail that you will that is normally provided is So again this reinforcement gets bent. So again, as you can see, this is the additional flexural reinforcement which increases the capacity, flexural capacity locally at the beam column face, so that plastic hinge doesn't occur here, because if the plastic hinge has to was to develop here, because the maximum moment is indeed at this place, then this steel, reinforcing steel, will yield, and uh, that yielding, there is no control on the propagation of this yielding inside this beam column junction. And when this yielding penetrates into this beam column junction, that may lead to deterioration of the bond strength. Obviously, there are compatibility issues. I mean, there are more deformations, more strain that needs to be countered, and that may weaken the bond, and that will affect the shear strength of this beam column junction, and that will be very, very critical. We can never allow any compromise on the strength of this beam column junction, and therefore we provide these additional reinforcing details such that the hinges, plastic hinge, begins to develop uh, a distance away, if typically one effective depth away from the beam column face. So I'll stop here today. Uh, Tomorrow we will discuss about the design for the shear strength of the beam, and also the uh, column design. And after that we will come to this beam column special issues related to beam column junction.